Okay, so we're gonna look at just now something called chromatography, and put simply, that is just a way of separating mixtures of chemicals. It does it through the fact that every type of chromatography, we're going to look at a few, has something called a mobile phase and it has something called a stationary phase. A mobile phase is like a solvent or gas which will dissolve the mixture and make it move, and the stationary phase will be a substrate, which is basically just like the material that you're using. It might be a solid or a liquid. So in paper chromatography, which you're going to see today, it uses a sheet of paper which is basically placed into some water. The water will move through the paper, and it moves the mixture through the paper. So the paper doesn't move on its own. So that is a stationary phase. So those two words are quite important. So it's important to understand the difference between those two. And chromatography is something you've probably seen before, maybe first or second year. You maybe use paper chromatography where you put like little bits of ink and then you've seen the different dyes that were in it. We're going to have a look at that today. So the explanation for chromatography is that separation occurs as the molecules in the mixture will be different sizes or they have different polarities. The molecules will move by different speeds because of these, and they will move different distances, and we're going to be able to explain that by these next two sentences. For example, large molecules will be difficult to dissolve and may move slowly. So if you were talking about the difference between a large and a small molecule, then the large ones are going to be moving more slowly, they won't move very far, whereas the small ones will move a lot quicker and they'll move a lot further. Or you might have something to do with the polarity. So molecules are more polar, they might have hydrogen bonding, they may stick on to the stationary phase. These parts of the samples will only move a short distance, so they might move very slowly. So for example, if you had a molecule with hydrogen bonding, that's not going to move very far, it's going to be stuck to the stationary phase, so that's going to be quite slow. You'll find that near the bottom of your kind of chromatogram, whereas one that didn't would be moving a lot faster and a lot further. And the same is true for sizes. If you've got a small molecule, that's going to go really fast, it's going to be further along, whereas a larger molecule would be stuck, not because it sticks to it, but it's just because it's more difficult to move. So that would be near the bottom and it wouldn't travel very far or very fast. So we're going to have a look at paper chromatography, and that's the simplest version. The stationary phase, which is what I've just said, is the paper, okay? And you'll get to see that in the video that I'm just going to show you. And also we've got the mobile phase. The mobile phase is a solvent, so it might be water or ethanol. I use water in the video. Some paper chromatography, and basically, as we've said, chromatography is a kind of a technique which can be used to separate mixtures, and we're going to have a wee look at paper chromatography just now. So what I'm going to do is, I've got a beaker of water here. I've not got enough a lot of water, I've just got enough to cover the bottom of my piece of paper I'm going to put into that beaker. What's going to happen is we've got a mobile phase and a stationary phase. He said that the mobile phase was the phase that moves. So what you'll see is the water actually starts to move through the paper, bringing the things that are in the mixture with it. So that's mobile because it's moving. We've also got the paper, which doesn't move, so that's a stationary phase. So what I'm going to do is, with my ruler, I'm just going to draw a line at the bottom of the paper, maybe like a centimetre up from the bottom, where I'm just going to draw a line where I'm going to draw my dots with my pens. My pens here, they will be a mixture. We've got two kind of blue colours here. Don't know if you can see that. They're both blue, but they're different colours, and that will be because there's a different mixture of inks in them. So I'm going to make a dot with both pens, just enough that it kind of dots a wee bit. I'll do it with both pens, and what we should be able to see is this mixture separating out. I'm going to fold the top of the paper over a wee splint I've got here. I don't know if you can see that, and that is going to be used to hold the paper out the beaker, and I'm going to dip that in. You can see already that the water is beginning to move through the paper, and it is actually separating the inks into the different colours. So pen ink is actually a mixture of inks, and those were both blue. We can actually see that they've got kind of different colours here. Obviously the darker pen has more kind of purple and stuff in it. You can see a definitely a purple colour in it, whereas the lighter blue, only had really a kind of blue coloured ink in that, which you can see is also present in the darker one, which is on the left. So let that sit for a wee while, and you can see that those inks have travelled as much as they're going to travel. So what's happening is the water's rising through the paper. That separates the mixture because some of the different parts of the ink will travel different amounts because of the way they're attracted to the water molecules that are moving through the paper. As that goes up, depending on kind of how you're doing it, you could let it kind of go the full way. If you leave it too long, the ink start to kind of make a mess over the page. You don't want to leave it too long, but you'll take that out. I will probably take that out about now, and then you mark on the piece of paper where the water got to, and that's called a solvent front. So I'll let that dry off, and then I'll put a picture on of the finished result. Okay, so we've seen my paper chromatography, and we've also seen my completed photo of it. So you can see that the kind of dyes have separated out. The blue dye kind of went to the top, the purple dye was present in both. Actually, you can see from the thing that they both had the same kind of dyes in them. There was a purple and there was a blue. The darker pen actually had more of the purple, and the lighter pen had more of the blue in it. So this is what happens. The water goes through, and as it goes through, it kind of separates the mixture. So we've got these two spots here. That was our start line, which we'd marked on, and then this line is a solvent front. That's where the water or the solvent gets to. That's going to be called X and Y, and this is actually a calculation that we need to be able to do. RF just means retention factor. And it's a distance, it's a measure of how far something travels relative to the solvent. So it's important that you might need to use, you will probably need to measure these in the exam, so make sure you take a ruler with you. Basically, we might measure this here. This one might be, say, 10 centimetres, and this one might be 8. You would use your ruler to work that out. So the RF for this one is going to be 8 divided by 10, so that's going to be 0.8, and it doesn't have any units. So basically, you need to know this this equation. It should be given to you in your data booklet. If not, then it's probably important to remember. So let's have a look at 2D paper chromatography, and this is what we saw in the video. Basically, we've seen it kind of separate into its two mixtures. However, we can actually do this more complicated in 2 dimensions, so we can run the chromatography in 2 directions. You can take your paper that you've done after it's been after you've done the chromatography, and you can see there's 2 spots here. However, what I can do is I can then split it, I can turn it around and then develop it a second time, just like this. And what actually happens is we find that there's actually 4 substances in here, but it just happened that the brown and the red had the same RF value, so they travelled the same amount. That could have been because they were equally as polar, or they were the same size. However, when you do it again, maybe used a different solvent or maybe use the same, it's actually discovered that these are actually different components. So sometimes it's necessary to do a 2D. We can use chromatography for following reactions to see if they're complete. Obviously, if it's complete, then you would only have 1 spot. If it wasn't complete, then you would maybe have mixtures of chemicals, your products and your reactants. So that's not so good if you were wanting it to complete. So that would have like 2 spots or 3 spots. So ideally, that's how you would use that. You can identify any reaction byproducts. So maybe something's going on and you've got something extra. So you know the reaction is finished, but there's maybe 2 spots. That means you've maybe produced 2 products. So that would let you do more investigation to find out what the byproduct is. And you can also check if there's any contaminants or impurities present in a sample, for example, during drug testing. So if you were to maybe do testing for testing maybe drugs, then sometimes they can have impurities in them, and that would show up as a different spike on a chromatogram, which you'll see later on. We can also use a paper chromatography, which is a TLC, and that basically just means instead of using paper, using a very thin layer of sand on a glass plate, and the water just moves through that the same as it would a piece of paper, but it's slightly, it's much better than the paper chromatography in practice. This is a more complicated one. This is called a gas-liquid chromatography, and basically what happens is you've got the mobile phase, which is an inert gas. It could be unreactive. So examples of this might be the noble gases. So you might have helium, you might have neon, you might have argon, for example, and nitrogen as well. Even though it's not a noble gas, it's not very reactive at all because it's got that nitrogen-nitrogen triple bond, and I'll write that up here. Which is very unreactive because it's very difficult to break that triple bond. The stationary phase is like a high boiling point liquid which is absorbed into an inert solid inside a long coiled column. So that's a column in here, and that's long and coiled. It might have something coating the inside, that liquid, and that just kind of goes along that. So what will happen is you can see a wee injector port here. What happens is a needle kind of goes into that. The gas goes through, and whatever you've injected through the needle is kind of picked up by the gas, and then that goes round. And obviously, as it goes round the column, the ones that are going to move quicker, so the small molecules, or the ones that are not very polar or have hydrogen bonding, they go really quickly, and that would end up going through the other side quite quickly. Whereas the ones that do not have hydrogen bonding, sorry, I think I've just said the wrong thing, so I'm just going to go back just to make sure. So if it's like a small molecule or one that's not got any hydrogen bonding, then they're going to go quite quickly because they're not getting stuck to the inside of this column. However, the ones with hydrogen bonding or much larger molecules, they're going to go a lot slower through that column. So what that means on your recorder is this is going to be the quick ones, and this one is going to be your large molecule, your slow molecules. These would be non-polar or small molecules. These ones would be more polar or large. Okay, so that just gives you, like, obviously the ones are taking longer to come out, because this is time along here. So the quick ones are obviously near the start and the slow ones are near the end. So here we go, this is like an example of this. A typical chromatograph indicates the quantity, so this is up here, and that basically tells you how much of something you have. If the peaks are high, then that means they're going to be, there's a lot of stuff in there. If the peaks were relatively low, then it means it's not going to be an awful lot in it. And we've also got this retention time, so this was like, we would use that for RF. So instead of measuring a distance, you would measure time instead. And that's the time for the sample to reach the detector after you've injected it in at the start. Each peak represents a different component in the mixture. So it's a wee bit like a chromatograph that we have done using the paper one, and you see different spots. Here it'd be like different peaks. So each peak you see here is a different component in that mixture. And we also have this thing called Hplc, which is high performance liquid chromatography. That's a similar technique, but it doesn't use a gas. So retention time gives you information on the components if you know the stationary phase. For example, if it's a polar liquid, and this is where it gets a wee bit more complicated, if it's a polar liquid, then the polar components of the sample will be attracted to the stationary phase and they will remain in the column longer. So it's going to have a longer retention time. However, if it was non-polar, it would not be attracted to the stationary phase and it will go further through very quickly. Normally a known sample will also be tested at the same time for a comparison with the sample being tested and investigated. So they might put the pure stuff through so you know the kind of retention times, so you can work out what each things are, and then you would put your kind of mixture through, and then you would match up the retention times to find out what they are. Okay, so what we're going to look at is we're going to look at this investigation, and basically the top sample has come from a chair, which was the starting point of a fire. The other chemicals, other chromatograms come from the chemicals which may have started the fire. Can you work out which chemicals were present in or on the chair? Okay, so let's have a look at it. Obviously, if we look here, this spike is quite important, and we can see that comes up in the paint thinner, and it also includes this kind of stuff at the end as well, about here and about here. That has the same pattern, which tells me that I have definitely got this stuff in here. So I definitely have paint thinner in that chair. Also, if I look at this kind of peak here, I can see that comes from here. So I've also got lemon fresh. I do not have any of the tung oil furniture polish, so that is not in it. I can't see anything from that chromatogram in this one, so I would say that that's not present. So hopefully that makes sense. The main things about chromatography are going to be RF values, the mobile and stationary phases, and obviously the fact that you can do 2D chromatography, where you might have had a mixture where you've got maybe two spots that actually have the same RF value, so show up as one spot. However, when you flip the paper over, then it shows up two spots. So that sometimes happens. Hopefully this makes sense. There's going to be some questions for you to work through. If you get stuck, you can ask your teacher, just send a wee email or send a wee message on Teams. But hopefully that makes sense.